Okay, I'm going to assume that we got through the other slides, and I'm going to start this lesson because this is where I hope you're going to be able to start on Thursday. So let's see if we can get this done. All right, so it says identical boxes that are filled with different objects are initially at rest. Horizontal force is applied for 10 seconds, and the boxes move across the floor. The mass of the box with its contents and the net force acting on the box while the horizontal force are applied is given in each figure. Okay. So I have A, B, C, D, and I want to see what they want me to do. It says rank the change in momentum during the 10-second interval for each box. Well, I know that a force applied over a period of time is going to cause a change in momentum. So I just need to look at my force acting on my object. Okay, so it's going to be a 10-second interval. So that's going to be 10 seconds for everybody, but the force is going to change. So the one that's going to experience the greatest change in momentum is going to be created by the greatest net force. So 10 seconds times 100 newtons. 100 newtons is 1,000 newton seconds. This one is going to be 50 times 10, which is 500 newton seconds. This one is going to be 75 times 10, which is 750 newton seconds. And this is going to be 75 times 10, which is 750 newton seconds. So I'm going to say that they want me to rank the magnitude of the change. So I'm going to say that the change in the momentum of D is greater than the change in momentum of B, which is equal to A, which is greater than the change in momentum of C. Now, let's see if we're good to go, and then we'll talk about why Ms. Walker got it right. All right, so let's go on to the next one. All right, so D is equal to A, which is equal to B. I'm sorry, D is greater than A, which is equal to B, which is greater than C. The time is the same for all of them. So the magnitudes of the momentum changes, which is Ft, will be, right, let's go back, will be proportional to the net forces acting. So I didn't pay any attention to the mass because if you look at it, M delta V is equal to F delta T. So this was 10 seconds for all of them. I looked at the force, and whatever I multiplied there would be equal to the change in momentum. Now, if I paid attention to the mass, I could find the change in velocity, but that's not what it asked me to do. So I'm good to go. So I'm going to get rid of that, and we're going to move on. All right, so let's go to the next slide. Now, this one says that we have a 1,000-kilogram car moving at 30 meters per second, so its momentum is 30,000 kilogram meters per second because it's 1,000 times 30, can be stopped by a 30,000 Newton force acting for 1 second, so that would be a crash. Or I could let it slowly come to a stop by letting my force be applied for 10 seconds, which is what you would do when you put your brakes on, and my force would only need to be 3,000 newtons. Now I'm going to try this. I don't know if it's going to work. One never knows about these things with technology, but we're certainly going to see if it will work. My home doesn't seem to have very quick internet, so we shall see what happens. So let's look and see if it's going anywhere. Trying. Not sure that I'm seeing anything. So I think that we're just going to go back to our PowerPoint and say, I'll have to show you that in class. My apologies. So let's go back here, see what's happening. All right, so let's move on to the next one. I will show you that in class. All right, so this one, yeah, it'll go, we'll try. But I definitely want you to see this one, so you're going to remind me on Monday that I wanted to show it to you because it's pretty crazy what happened to you. So let's escape and we'll see if we have anything over here on the lovely little internet. Maybe we do. Oh my goodness, I think we're getting something. All right, so just watch what happens here because it's pretty insane. So if you think about what was going on there, evidently for some odd reason, this man thought it was a good idea to be on his laptop when he was driving down the road. And you and I both know, you've seen them, they're putting on their makeup, they're reading a book, all kinds of craziness goes on. So pay attention to the people next to you, please. They can be very, very dangerous. All right, another application of impulse. So contact time is reduced if the arm's deceleration is kept as small as possible. This is done by using follow-through, which means to continue to push through the contact period. I think your coaches talk to you about this if you play golf or tennis. Keep that ball in contact with the club or the racket as long as possible. It's simply called follow-through. So what happens is if I want to minimize the effect of the force on an object involved in a collision, I want to make this be really, really large. If I want to maximize the force, as in tennis, I want to make this be, I'm sorry, we should have said tennis would be the long period of time. That's why they call for a follow-through. This one, if I want to maximize the effect, such as taking this guy's lights out, I want this F to be as large as possible and this time to be as short as possible. All right, the vector nature of momentum. Change momentum of a ball that is dropped onto a rigid plate. So if you look at it, the ball comes down and hits the plate and pops back up. So it's moving down, so that's its velocity. We could call that positive if we wanted to, and then it pops back up and we could call that negative. It doesn't really matter what you call it. You just must recognize that these are moving in opposite directions because that makes a big, big impact on your math. All right, so if we look at this, it says that we have a ball that's 2 kilograms, strikes the plate with a speed of 20 meters per second and goes back up with a speed of 15 meters per second. So if I wanted to work this problem, I would say that P is equal to M delta V. Well, P is no big, M is no big deal. That's 2 kilograms. All right, your delta V is going to be your BF, which is this puppy right here. I'm going to make that positive, minus your BI, which is negative. So 15 meters per second minus a negative 20 means that the change in velocity was 35 meters per second. Now, if you didn't pay attention to those signs, you would have said 15 minus 20 is 5, and you would have gotten the wrong answer. Pay attention to the direction. So that's 35 meters per second. So the change in momentum, delta P, is equal to 70 kilogram meters per second. Okay? So that's what they're looking at there. Let's mouse back and see if the little PowerPoint tells us the same thing. There we go. So it works. You have to pay attention to the sign or it will be disastrous. Okay, now we have a 500-gram baseball loose to the left at 20 meters per second. The bat is in contact with the ball for 0.002 seconds and it moves the ball in the opposite direction at 40 meters per second. What's the average force on the ball? Well, here's what I know. I know the mass is a half a kilogram. Do not leave it in grams, please. The change in time was 2 times 10 to the minus third seconds. The initial velocity was, I'm going to call that to the left, negative 20. The final, opposite direction to the right, positive 40. And they want to know F. Well, F delta T is equal to m delta v. So F times 2 times 10 to the minus third is equal to a half a kilogram times, okay, VF we said was 40, minus a negative 20. So that's going to give me 60, positive 60. Half of 60 is 30. So if I take 30 kilogram meters per second and divide it by 2 times 10 to the third, minus third, sorry, that should give me my force. So 30 divided by 2 is 15 times 10 to the third newtons, which is the same as saying, I think, as 1.5 times 10 to the fourth newtons. Okay. So you can pause it if you need to, but that's what's going to be my average force. All right, now that's going to go away when I hit the mouse button, but we'll go through the PowerPoint and see what they do. So here's our PowerPoint. So we have that and that. And if we continue it, and again, you can pause it. Wow, we get the same answer as Miss Walker. So it's 15,000 newtons. It's positive, which means it's to the right, and that makes complete sense because that's the direction that the object's moving. All right, so the problems, the Big Mo worksheet 1 through 8, problems due tomorrow. Okay. And I'm not sure when our conservation of momentum lab is. It'll be a formal lab. It's on your activity sheet. I don't know. I'm going to keep on recording because, actually, let me see how much time we have left. No, I'm not. I'm going to stop, and then I'll start the next lesson. Okay. So if I hit the